Thank you very much for having me. And just in terms of going forward, I'm very happy to take questions. It's also almost easier if you just start asking rather than raising the hands because I might not see it, etc. Yeah. So I'm very happy to present my paper, which is trying to work with Ellen Muir, who's at postdoc at Harvard in transition to MIT. So the paper is called Optimal Hoteling Auctions. As a little motivation, auctioneers or designers very regularly sell multiple items or multiple goods, heterogeneous but horizontal differentiated goods at the same time. So that includes artwork and radio spectrum licenses and advertisement search keywords. And so that raises the question, what is the best way for doing so? That is, what is the optimal selling mechanism? And what we do in this paper here is we consider standard hoteling model. Just bear in mind that we'll be looking at the single seller who owns objects on both ends of the line. So there's a multi-product auctioneer who has objects at 0 and objects at 1 for sale. And consumers, buyers have single unit demands and draw their location on the unit interval from some commonly known distribution, which is the same for all the agents. And they have linear transportation costs, that is common knowledge, as is the whole payoff structure. The only thing that is private information of the agents is the thing that is private information of the agents is their location on the 0-1 interval. And so for this problem, we're going to derive the optimal selling mechanism, that is the mechanism that maximizes the multi-product auctioneers' expected revenue subject to the incentive compatibility and individual rationality constraints of the agents. And to give you a high-level summary, so there's too many things maybe that I want to get across at the same time, but the right-hand column contains a simple case with a single agent and uniformly distributed types, and the left-hand column gives you a summary of the main findings or some of the key findings. So in general, the selling mechanism is going to be inefficient, and that is so even when you have full market coverage, that is, you sell to every type, and even if you sell to all consumers, even if you have enough goods to serve all the consumers, and even if you do serve all the consumers, the mechanism in general is going to be inefficient. And this inefficiency arises because of randomization of agents. You do deliberately the auction, it deliberately sends agents, allocates the wrong good to the agents in some sense. So if you look at the right-hand graph, that's for a uniform, for a case of uniform distributions with a single agent. And the V is the gross value of the consumers or of the consumer for the good. And what you do when V is larger than a half is you serve consumers between 1/4 and 3/4 a lottery ticket by which they send left and right with equal probability. So their expected transportation cost is a half. So you can completely rip them off by charging them V minus a half. So they're indifferent between participating and not. And then you can charge a premium price by which you guarantee that the agents, or by which you promise the agent to get good 0 or good 1 for sure, and you get a premium price for that certainty. And so these are the premium prices, P0 and P1, which are larger than V minus a half. And consumers types who are close to 0 are willing to pay P0, and consumers who have types close to 1 are willing to pay P1. And so that's for the single case, but it gives you an intuition for how you for why you want to use randomization and how you can do better. With multiple agents, the problem becomes much more complicated because you have to keep the probabilities, balance the probabilities in the right way, so that you still get these 50-50 lotteries in the right places. So that's the combinatorial complications that arise. That's part of the problems that arise in the general problem. And then we also show that there's a two-stage clock auction implementation of the optimal mechanism. So in the first stage, the bidders submit kind of coarse preferences. They just say, I want to bid on good 0, or I want to bid in the lottery, or I want to bid on good 1. And if there is excess demand in that first stage for one of the two goods, you just run a clock auction for the good that is in excess demand. So that's the two-stage clock auction implementation. And then for some environments, we also show that there's there are asymptotically optimal prior free mechanisms that permit clock auction implementation, whereby asymptotically optimal prior free, we mean that if you look at replica economies, right, you replicate the number of goods 0, number of goods 1, and the number of agents that are there. And if you let these replicas go to infinity, then asymptotic optimality means that in the limit, you get as much revenue per capita using a prior free mechanism as you would if you knew what the distribution is. And this, in some special case, this asymptotic optimality gives rise to personalized pricing, where the prices I face are going to be different from the prices Marion faces, because the prices that are used to determine that I face are used by using the reports from all the other agents other than me, and likewise for Marion. Okay, so that's sort of the summary of the high-level summary of what we do. Brief literature review. In some sense, this is a generalization of Meyerson's optimal auction to the case where you could be selling, if the gross value V is large enough, you don't have independent auctions, so the two auctions at 0 and 1 are going to interact. So for the IID case, it's a generalization. So the thing where Meyerson's optimal auction is more general is, of course, that he allows for heterogeneous distributions across the agents. Single agents problems of the hoteling model with uniform distributions have been studied previously in the marketing literature by Zhang, and using a mechanism design approach by this paper by Ballesteros, Malkoff, and Lea in the Journal of the European Economic Association. They generalize things in a different dimension than we do. So they assume a single agent uniform distributions, but they allow for alternative cost functions of transportation, whereas our take here is going in the direction of finitely many bidders and channel distributions. And there's a sense of opaqueness that also arises with vertically differentiated goods, such as we analyzed in the JP paper. Then there's a tight connection to the literature on countervailing incentives that started with Lewis and Sappington. And to me, very surprisingly, the closest or a very close connection is the paper on optimal partnership solution with Cedric. I just didn't anticipate that there would be this type of a connection here. And I mentioned the Kramp-Gibbons-Klemperer paper because that's kind of the mother of all these partnership papers. And then last but not least, last anyway, there's a literature on prior free asymptotic optimal mechanism design. And here again, there's going to be a connection to a two-sided clock auction that is prior free and asymptotically optimal that Leslie Marks and I worked on and published a couple of years ago. And I just didn't see how you could get in this hoteling setting, how you could get a double clock auction being asymptotically optimal. But hopefully that will become clear as we go on. Okay, so there are no questions. Let me proceed to the setup, which at this high level should be very very simple. So we consider a variation of the hoteling model where the auctioneer has K0 goods for sale at 0 and K1 at 1. So that's the capacity that the seller has. And there are capital N risk neutral buyers. As I said, the buyers have single unit demands and gross value V. That's the same across all the buyers. If your location is X, somewhere between 0 and 1, your gross utility or your willingness to pay for the left good is V minus X, and your willingness to pay for the right good is V minus 1 minus X. And so if the buyer is allocated good L with probability little QL, and Q0 plus Q1 is not bigger than 1, then the expected payoff of that buyer is Q0 times V minus X plus Q1 times V minus 1 minus X minus T, where T is the transfer. So even though it's a hoteling model, T stands for transfer, for the transportation cost, which is taken to be linear with a constant marginal cost of 1. The opportunity cost for selling for the seller is 0, and the value of the outside option for the buyers is also 0. Okay, so a typical agent is denoted by little n, and your realized location is your private information. The distribution here is denoted by capital F with a positive density, little f. In the paper as the talk, we focus on the IID case. For the purposes of the talk, we assume that the distribution is also regular. And some of the results, some of the asymptotic optimal prior-free results rest on regularity, but that can be easily relaxed. So what does regularity mean? It means that these two functions, psi b, which is called the virtual value function, and psi s, which is called the virtual cost functions, are monotone functions. Notice that for any x, it's always the case that psi b is less than x, and well, for any x in between 0 and 1, psi b is less than x, and psi s is bigger than x. And for example, if f is the uniform, then the virtual value is just 2x minus 1, and the virtual cost is 2x. So even though we impose this regularity, the problem is not going to be regular in the sense defined by Meyerson, as we will see. Okay, so we're going to look at direct mechanisms that are without loss of generality, and they're parameterized or described by an allocation rule Q. That's a mapping from the set of possible reports, right? With n agents, any agent can make a report between 0 and 1 to the probability distribution over the possible allocations, which is you could get 0, 0, you could get good 1, or you could get good 0. And the transfer rule is a mapping from the reports to the real numbers. We use this little QNL to denote the interim expected allocation or interim expected probability, interim probability, I suppose, of obtaining good L when you report the type, or when agent N reports the type X, assuming that everybody else reports truthfully. So this is the expectation with this, or the random variable with respect to which you take the expectation. And likewise, little tn is going to be the interim expected transfer of that agent. Okay, and the feasibility constraint is that ex post, you never allocate more than you're endowed with as an auctioneer. Okay, and yeah, so this un of x and x hat is the utility that you get when your type is x, and the expected utility you get when your type is x and you report to be of a type x hat. And un of x is the utility you get when you report your type x truthfully. And so then incentive compatibility means what it usually does, right? Which is that reporting truthfully is better for all possible types and reports. than reporting a lie. And individual rationality means that you're better off weakly participating in a mechanism than walking away. And the aim of the game here of our game is to find mechanisms that maximize the designer's ex-ante expected revenue subject to IC and IR. Okay, so now the first thing that pops out of the analysis of incentive compatibility, right? What does incentive compatibility, what kind of restrictions does it impose? It says that the first part is that the kind of the standard monotonicity property, which is that the probability of getting good 1 minus the probability of getting good 0 must be decreasing in X weekly. So as you report a higher type, you must be weekly more likely to get good 1 rather than good 0. So this only restricts the difference between the two allocation rules, and in the problem where we have partial market coverage that creates additional degrees of freedoms that are a little bit tricky to take care of. And then the second part is that the allocation rule kind of pins down the transfers by this envelope theorem kind of formula. Okay, so now we're going to call X hat an arbitrary critical type, right? This you can choose that arbitrarily. The expected transfer you're going to get from the agent, it can then be written as this integral from 0 to X hat, integrating over this term, plus the integral from X hat to 1, integrating over this, minus the interim expected payoff or interim expected utility of the agent of type X hat. So this is just the standard formula. It's a bit more complicated here because the allocation rule is two-dimensional. But this should be familiar for anyone who's seen some auction theory or mechanism design before. Okay, so now we want to go from this formula here to an expression that involves the kind of the virtual types or appropriately defined virtual type functions. Okay, so we denote for a given a critical type X hat, we denote by psi naught the virtual value or the marginal revenue associated with getting the left good, and by psi 1 the virtual value associated with getting the right good. So if you use these definitions, and they're defined in a piecewise way, right? So to the left of X hat, you use the psi S, and to the right, you use the psi B. Okay, once you use these two virtual type functions, then you can write the revenue that you're going to get from a mechanism consisting of the allocation rule Q and the transfer rule T. This becomes this formula here. And so very similarly to what occurs in the optimal partnership dissolution problem with that we analyze with SEDIC, you're going to get a component of that revenue that consists only of the allocation rule and the critical types X hat. And then there's an additional term which is separable and consists of depends on the X hats. And so this thing here, this R tilde of Q and X hat, that's what we're going to call the virtual surplus function. Okay, and so what we're going to show here is that you know, even though these things, the Q's and T's are intertwined, because the worst of types or the critical types are going to somehow depend on the allocation rule. We're going to have a separability of allocation rule and transfer rule in the following sense. So the optimal mechanisms satisfy a saddle point property such that the worst of types minimize the virtual surplus over the critical types, and the optimal allocation rule maximizes that surplus given those worst of types. And so what that means, or what that is going to buy us, is that we can first solve that saddle point problem. That gives us the optimal allocation rule, and then once we have that allocation rule, through the envelope formula, we get the transfers. So that's the separability of allocation rules and payments or transfer rules that we're after. The other problem is that, as I alluded to, the incentive compatibility imposes monotonicity constraint only on the difference between Q0 and Q1, how that must vary in X. But it doesn't independently restrict the Q0s and the Q1s. And in the problem that we study in the paper as well, but that I shall not talk about more for the rest of this presentation, is if you have partial market coverage, then it is without loss of generality to look at mechanisms such that individually these probabilities are monotone. And the lotteries that arise as a result of ironing that pins down the ex post allocation as a function of a single parameter. Okay, now let me try to illuminate what is the fundamental property of these optimal mechanisms. So for any given allocation rule Q that is monotone in the desired sense, we denote by omega n the set of worst of types, the set of types for H and N that minimize the interim expected utility. And then this omega of Q is the product set of these worst of types. And the result is that the set of worst of types is the set of critical types that minimize the virtual surplus. That's going to be the connection between these critical types and the worst of types, right? The worst of types is the set of minimizers of that virtual surplus. And with that at hand, you can write the expected revenue for a mechanism with an allocation rule Q and a transfer rule T as the difference between the virtual surplus evaluated at these worst of types minus the sum of these interim expected utilities. And in an optimal mechanism, that you're not going to leave any money on the table, so you make the IR constraint binding. So this term here will be 0. And so then the rest of the argument here is to show that as you want to maximize this here over Q, accounting for the fact that the omega also is going to depend on the Q. The result here, which mirrors the result in the partnership problem with SEDIC, is that the saddle point Q star omega star of R tilde is such that Q star is the maximizer of R tilde for a given omega star, and omega star is the minimizer of virtual surplus for a given Q star. And moreover, the allocation rule is unique, or the saddle point is unique in the sense that if Q prime is optimal, then it also has to be a saddle point. Okay, so this seems, or this is a problem that also applies in standard, or this is a property that you would also have in standard mechanism design problems such as an optimal auction, or an optimal procurement auction, or an optimal two-sided mechanism such as for a Meissen satisfied problem. There, the simplicity or tractability derives from the fact that a priori, simply by incentive compatibility and the envelope theorem, who's going to be the worst of types, right? For the buyers, it would be the lowest possible type. For sellers, it would be the highest possible type. And you don't need to know anything more other than the monotonicity property of the allocation rule. But here, for any monotone allocation rule, or for different monotone allocation rules, you're going to have different sets of worst of types. And so that's what this theorem buys us. And that's what gives these kinds of problems tractability, I will claim, that the fact that we can find this saddle point And then once we have found the saddle point, we know what's kind of the optimal allocation rule, and then we can find the transfers. Okay, so let me now walk you a little bit through the specifics of, or two specific applications of, or derivations of the optimal auction. The paper is more general, but here we'll be focusing on the full market coverage case, by which we mean the situation where a monopoly seller at zero would sell, if he has enough goods, he would sell to a buyer at location one, and likewise a monopoly seller at location one, a single product seller would be selling to a buyer at location zero. So a clearly very sufficient condition for this here is that V is larger than this term here. And so the paper covers the partial market coverage case, which is more complicated.
Sorry, I had a quick question.
Yep.
Do you think that the saddle point property is emergent from the fact that preferences are single peaked in the goods? That is, if you do a general multidimensional screening problem with single peaked preferences, would a similar property emerge?
That is a very good question. I haven't thought about that. Let's see. I need to think about it. You know, I don't see the same property holds in the partnership problem, and there I don't quite see what single peakness would mean. Does it, you know, it's a homogeneous good, and the more you get, the better. So I suppose it also has single peakness.
Right.
Yeah, it's a great question, but I don't have the answer to that. Yeah, it's on the to-do list, exploring, finding out, you know, how channel, what are the bounds of that saddle point property, or how channel is it? Yeah. Okay, and we'll be looking here at two special cases. One is what could be called n single agent problems. That is, you have enough goods at zero and at one to satisfy all the agents. So in the sense that the minimum of Q0 and Q1 is at least as large as n. So then you can just think about having n single agent problems. And the other problem that we'll be talking about is the kind of a converse of that, where you just have enough goods overall to satisfy all the buyers, but no more. So Q0 plus Q1 is equal to n, and that's what we refer to as the balanced market problem. And here you have, in the single agent problem, you have an extreme abundance of degrees of freedom as a designer. And in the balanced markets problem, you're going to have 0 degrees of freedom, and that's going to affect the optimal selling mechanisms. Okay, so let's first look at the single agent problems. So we can drop a subscript because we just look at one agent, right? And there's not going to be a difference between interim and ex post relative to the reports of everyone else, because what you're going to get is only going to depend on your report. And because we have full market coverage, we know that Q0 plus Q1 is going to be equal to 1. And so we can work with a single parameter, which we denote, a single variable, which we denote Q of X, which is the probability that you're going to get the left good, meaning that with probability 1 minus QX, you're going to get the right good. And then incentive compatibility means that Q has to be weakly decreasing. Okay, and so then for a given critical type X hat, we can write the revenue that you get from a single agent as this term here, where this up to here, this -1, this is the virtual surplus. Below here, it says what this psi function is. And you subtract from that the utility of the critical type U of X hat. And so this psi function here is the net revenue that you get from sending an agent to the left rather than the right. So this is psi naught minus psi 1. Okay. So this is that thing. Now, because psi S is larger than psi B, whenever you reach X hat, this function big psi will have an upward trump at that point. And so this function will fail to be monotone, and therefore we will have to iron it. Okay. And so each critical type X hat uniquely pins down an ironing parameter denoted by Z. And so we can write psi bar of X and Z as being equal to 1 minus 2 times the virtual cost for X less than some threshold, X lower bar, which depends on Z, equal to Z for all the X's within this kind of ironing range, X lower bar to X upper bar, and equal to 1 minus 2 times the virtual value for X's that are larger. And the X lower bar of Z and the X upper bar of Z, they satisfy this equality here in terms of expected values. This is where you see that regularity, or maybe, well, hopefully you see that the regularity assumption is going to be useful here, because we can just simply take the inverses. So X lower bar of Z is equal to this here, and X upper bar of Z is equal to this here. And so X hat of Z is the critical type associated with a given ironing parameter Z. So this is the ironing procedure. And so what we plotted here is I was too quick. Yeah, so we're going to use the critical type to identify the corresponding ironing parameter, and given the ironing parameter, there's a set of maximizers of the objective function. So to remind ourselves what we're after is we're looking for, or we're going to transform this psi here into a psi bar such that the pointwise maximizer is going to satisfy the monotonicity associated or required by incentive compatibility. Okay, and so if we have Z equal to 0, the pointwise maximizer here plotted in red is to send the agent to the left whenever its type is less than X lower bar. And then any allocation between 0 and 1 will be optimal in the ironing range, because the ironing parameter is equal to 0. And so you're indifferent between sending them left or right, but any other solution would also be a pointwise maximizer. And then when X is larger than X lower bar of Z, you're going to optimally send the agent to the right. But we need for the worst of type to be X lower bar, X hat, we need to take the selection in the ironing range that is equal to 1/2. So that gives you that 50-50 lottery for the type in the middle. And so this is the unique solution to this saddle point problem. And if you write this down in allocation space, so then you get Q star of X, that's the optimal allocation rule, and you get T star of X, that's given by this formula here. And so the agent who enters the lottery is pays V minus 1/2 and gets a utility of 0. If you get the premium product, you pay V minus psi S inverse of 1/2. If you get the 0 product, and if you get the 1 product, you pay this price here. The lottery price by construction does not depend on the distribution, because it only hinges on the 50-50 lottery and your transportation cost, which is linear. And so the lottery price will always be V minus 1/2. But the premium prices, they depend on the distribution. And if you look at the uniform distribution, which was the example that we had on the introductory slides, then you get indeed, if you plug in the formulas that we have, you get indeed a V minus 1/4 for the premium products, as we said there, and the X lower bar of 0 will be 1/4, and the X upper bar of 0 will be 3/4. right, I mentioned the abundance of degrees of freedoms that we have in this problem here. And so the ironing parameter set star equal to 0 is uniquely pinned down, entirely pinned down by an indifference condition for the designer, which is the designer. When the agent is in the ironing range, the designer must be, or the pointwise maximizer must be indifferent between sending the agent left and right. And so set star has to be equal to 0. So that's a stark contrast to the case of balance markers, which I look at now, where the design is not going to have any degrees of freedom. And here, the whole mechanism is going to be pinned down by the feasibility constraints, basically. Okay, so we maintain the assumption that full marker coverage is optimal. So that doesn't change the iron virtual type function psi b. And now the corresponding allocation rule parameterized by Z is going to be based on the ranking of iron virtual types. So suppose, and now it could be that the ironing parameter is positive, then you end up with an iron virtual type function psi bar that is of the shape here, and you have the agents bid, right? So the agents submit reports, and the way we have it here, we have two agents who bid outside the ironing range, two agents in the ironing range, and two agents who bid outside, above the ironing range, so to speak. And it still has to be the case that the interim expected allocation, when you report something, when you submit the report in the ironing range, is equal to 1/2, so as to get these 50-50 lotteries. Okay, and now this is where you can sort of get a sense of how things become combinatorially a little bit challenging. So for a fixed ironing parameter set and type report in the associated ironing range, we denote by Q bar of I and J the probability that this agent obtains good 0. And this probability will have to be equal to 1/2 for things to work out. So what are I and J? I is the number of agents who reported types below the ironing range. So that's here it would be 2 in this case. And J is the number of agents who reported types above the ironing range here, right? So that means that N minus I minus J minus 1 agents reported types within the ironing range. Okay. Nicely consistent with what I just said. Okay, so then this Q bar is given by this function here, right? Q bar of I and J. And now this, as I told you, it's going to be a combinatorial challenge, but this is going to be the probability that state IJ occurs for a given ironing parameter set. And so this is this formula here, where this term here is a multinomial coefficient of this form here. And so the interim expected allocation for an agent reporting a type in the ironing range is then given by this term here. And now it takes some work, but it can be shown that there is going to be a unique set such that this probability here is going to be equal to 1/2. This is what we're after, because this is we need to make this interim expected allocation equal to 1/2 so as to get the lotteries. And so what happens here for this problem here is that the ironing parameter is entirely pinned down by the feasibility constraints. And so you can have a positive ironing parameter. The ironing parameter can be 0, it can be negative, depending on the distribution and the availability of goods 0 and 1. Okay, so let me use the remaining time to briefly talk about the two-stage clock auction implementation, and then time permitting about the prior free mechanisms. And so if you want to think about two-stage clock auctions, it's useful to keep that picture here in mind, right? So you could be thinking about agents, or this is how the two-stage clock auction is going to work. There's going to be 3 reserves. One is a reserve for good 0, one is a reserve for good one, and one is a reserve for the lottery price now, or for the lottery. Now, the lottery reserve is going to be V minus a half, of course. And the other reserves are going to be determined in the way that you would expect. So we look at the balance market case here. So K naught plus K1 is equal to the number of agents. And the three reserves are, there's this lottery reserve, V minus a half. R naught is the reserve for good 0, and R1 is the reserve for good 1. And this is assuming we've solved the optimal mechanism design problem, and so we know what Z star is, and we know what X lower bar of Z star is. And so each agent is allowed to bid on exactly one reserve at that stage. And this is the first stage where you have kind of coarse bidding. You just bid on one of the two things. Yes, Peter.
See, Simon, first, sorry I arrived late. I just found out about this, and it's quite early here in California.
But it's very early here too.
Yeah, it's 1:30 in the morning. Are you in Australia,
yeah.
Melbourne? Yeah.
Yeah,
okay.
yeah.
So, I mean, what if if capacity is greater than n, are you going to consider that case? Or I was just wondering how sensitive it is, because it seems like, this is a fairly special case that they've, at least it seems to me. I mean, normally we think of when there's lots of goods and lots of people that, people have production costs and they can make more and that sort of thing.
So, which question?
So the question is, your first assumption there, that the number of goods is equal to the number of agents.
Yeah.
So how critical is that? Is, what if I had a production cost and I could make, I guess maybe it's not important because there would be, because of the unit demand assumption.
So the optimal mechanism, we can solve it in complete generality. So which way would you want to relax it? You would want to have more bidders than goods, or would have less bidders than goods?
I was either way. Yeah, I mean, it just seems like equal n is special.
Yes, it is, but given that I agree. The optimal mechanism, when you do not have that condition, but you have enough goods to serve all the consumers, right? That's something between the single agent problem and this problem here. It's going to be more complicated, but it's going to be a combination of feasibility that pins things down and design is a difference. And sometimes you will always have a lottery, but sometimes you may not sell one of the two goods as a pure good because you run out of it.
Right.
So that's the case for the full market coverage case for the optimal mechanism. But given that I didn't cover the other cases, I'm going to confine this treatment of the optimal.
That makes sense. I was just curious.
Yeah. No, it generalizes. It's not surprisingly a good question.
Excellent. Thank you.
Yeah, thanks. Okay, so right, so this is two-stage procedure. In the first stage, you have this coarse bidding, and each agent is going to bid on exactly one of the two reserves. And we denote by YL the number of agents who bid on reserve L, where now L is, well, as before, is 0 and 1. And if you bid the reserve RL, you take no further action. And so now we have to distinguish between the things that happen, but this is where the coarse bidding is going to be useful. So if it so happens that Y naught is equal to K naught and Y1 is equal to K1, you're done. Now everybody trades at the reserve and everything is finished. If Y naught is larger than K naught, which is going to imply that Y1 is less than K1, then you run a clock auction for good 0 until you have K naught minus 1 agents remain active. So there's something that you might not like as an auctioneer, because you're going to give up a little bit on the privacy of the K naught minus first agent who's going to win good zero. But you will need that information to determine the prices for the other agents who obtain a good one. Okay, and so the payments are going to be P naught of K naught plus 1. So that's the second to last agent, or that's the last agent to drop out of that clock auction for good zero. So that's what the agents who win good zero are going to pay. And the other agents are going to pay the kind of the lowest bid that they could have made while still obtain a good one, which is going to be this here. And this is maybe where you see how why we need to kick out the K naught minus first one guy as well, to find out what's that price here. And analogously for the converse case, where you have the other sort of imbalance. And then there's the case of how you determine the lottery prices, but it kind of follows in the usual way. So the lotteries are going to be, you need to adjust the lottery prices when both goods are under demanded, and this is kind of the way you do it. So we get this coarse language or simplified bidding language in the first stage, which I think resonates with some of the auction designs that have been proposed for combinatorial auctions, and it derives here from an optimal mechanism. We're not going to have obviously dominant strategies, but it allows the agents with dominant strategies, and this coarse information that you get from the first stage allows the designer to optimally price discriminate in the second stage. Here, this occurs with the pure objective of profit maximization. That's what we analyze, but you can show that the general insight generalizes to any Ramsey problem where you maximize a convex combination of social surplus and revenue. So unless your weight on revenue is zero, you're always going to have these lotteries for these kinds of problems. Okay, now I got about 3 minutes to talk about asymptotical optimal prior free mechanism, including providing a definition what that stands for. Okay, so famously, Wilson criticized this Bayesian mechanism design as not being detail-free and depending on the fine details of the environment. And so we heed that criticism. And now we're going to look at mechanisms that get you an optimal mechanism that, are going to be profit maximizing in the limit, but that do not require knowledge of the distribution. And so what we have in mind is like fix a problem characterized by distribution, a number of agents and a number of goods. And now we're going to look at eta-fold replicas of that, where we multiply the number of agents and number of goods by eta, but still assume that everybody draws their types independently from some distribution F. And R star eta will be the expected revenue of a designer who knows the distribution F given eta, using the optimal mechanism. And R eta is the expected revenue of an auctioneer who doesn't know the distribution F and uses some prior free mechanism given eta. And here the mechanism is going to satisfy dominant strategy, incentive compatibility, and ex post IR, which is the natural notion of equilibrium if you do not know the distributions. But the way it's defined here, the expectation is going to be taken with respect to the true distribution F, but the auctioneer doesn't have to take that expectation. And so we say that a DIC, a dominant strategy mechanism that is ex post IR, is asymptotically optimal if in the limit the ratio of these two things goes to 1, the limit as eta goes to infinity. Okay, and so for the balanced market problem, and assuming that V and F are such that full market coverage is optimal. So it's a joint assumption or restriction on F and on the gross value of the consumers. So then the statement here is that there exists a DIC ex post IR mechanism that is asymptotically optimal and that permits implementation via a clock or double clock auction. And so let me just sketch that mechanism. So here the X brackets thing, this is the lowest draw, or the eta K0's lowest draw out of eta N draws, and analogously. So these are order statistics that go from smaller to larger. And the way you proceed is you have a direct mechanism, everybody reports their types, and you start eliminating. You start, this agent is going to be kicked out, it's not going to get good 0, and this agent is going to be kicked out, it's not going to get good 1. So they enter the lottery. And as you start eliminating in that way, you can start estimating the virtual values and the virtual costs based on their reported types, using the spacings or the statistics based procedure that we had in the paper with Leslie in chat a couple of years ago. And as you drop out and participate in the lottery, your surplus is going to be 0. So this is as if you were dead, or as if you exited the auction from your perspective. So there's not going to be an incentive compatibility problem there. Now it boils down basically to estimating margin revenue, margin costs based on these on these reports. And in that sense, or for that reason, it becomes exactly like a double clock auction in a two-sided environment as Leslie and I studied. So that was a reasonably surprising connection that I really did not anticipate. And there's another, one thing that I would like to finish on, or a note I would like to finish off on, is a connection to personalized pricing. So rather than looking at the balanced market problem, let's look at the problem of when you know the distribution, you have n independent single agent problems, right? So this is this problem here. So if you knew F, you would have n independent single agent problems. And now you can look at the problem where all the agents report their locations, right? And now you can use the reports from the agents other than n, x negative n, to estimate agent n's distribution and to determine the prices that this agent is going to face. So the lottery price is clear, but what are the premium prices? That's going to depend on that distribution. But because these reports are outside of what the agent itself can affect, the agent is going to be a price taker. Therefore, this is going to be a dominant strategy, ex post IR mechanism. So if you then use an appropriate estimation procedure, such as what Baliga Vora proposed to estimate ident virtual types, you're going to have an asymptotic optimal mechanism. And so what I think is really nice about that insight is that it gives rise to personalized pricing where you use big data, so to speak. And the feature that you're exploiting is the fact that the reports of the other agents are not so much informative about my location, but they're informative about my distribution. And so that's what the designer will be exploiting here. Okay, so that's that connection to personalized pricing. Let me wrap up here on what we do, right? So this is a generalization of Meyerson's optimal auction to horizontal differentiated objects. The qualification is that we assume IID, identical distributions, whereas his analysis does not. Even with regularity, IID and full market coverage, the optimal selling mechanism is inefficient, but it does permit the two-stage clock implementation, and under some more stringent conditions, we get asymptotic optimality. I think there's many avenues for future research. So you could be thinking about the goods being of different vertical quality. V0 could be different from V1. Loosely speaking, I didn't define these things, right? But at this point, it was just V's. You could have heterogeneous distributions or gross values, heterogeneous across the agents for the two goods. And you could analyze, what's the optimal placement of the goods on the 0-1 interval. And maybe you could also look at the problem where the seller has a network of goods for sale and the consumers are distributed along the along the edges on that network. So that was what I had.